Now you might have been thinking, man, I wish you would have done some examples with all those formulas. And the reason I didn't do any was because I'm going to take all of those laws and I'm going to put them together in one easy to manage formula that can apply to any situation. And we're going to combine all these proportionalities into something that's aptly named the combined gas law. So all of those formulas from before, I'm going to put them together into this. And this is the one that you should memorize. Because I can be given any situation where I change a number of properties of a gas and be able to solve for a single new property. And what's even better is that if the problem I'm looking at doesn't give me some variables, so if I'm only given info on some variables, I'm going to assume the others are constant. And the best way to illustrate this is let's jump into an example here. So a gas occupies zero point 0.6 liters at 25 degrees Celsius. What will the volume be at 75 degrees Celsius? Okay. So first of all, what formula am I going to be pulling from? Here, notice that I'm causing some sort of change to a gas. And so I'm going to start by looking at the combined gas law. Now, the number one, or I should say the one on the left side, the ones, that's all my initial conditions. And the twos on the right side are the final conditions. So are there some things that I can cancel out that I don't need? Well, let's look at the problem. The problem gives me an initial volume, so there's V1, an initial temperature, T1, and then it's asking me what the new volume will be. Okay, that'll be V2. That's what I solved for. And it's giving me the second temperature, T2. So the problem does not mention pressure or the number of moles. So I'm going to assume those are constant. That means they're the same on the left and the right. And if there's something that's the same in the equation that's on the left and the right, what can I do with it? I can cancel them out. And notice this gets me to that relationship between volume and temperature. This is why I was saying earlier, like you don't have to memorize those other individual laws because we're going to put them all together for the combined gas law. And this will help you with any sort of problem where you're changing the conditions of a gas. All right, and now we're going to solve for V2. So let's rearrange this equation to solve for V2. And now we can start plugging in things. But first, before I start plugging in numbers, I need to address the temperature. Remember at one of the first videos we looked at, I talked about how gases need to be measured in degrees Kelvin when it comes to their temperature. So the problem gives us temperature in Celsius. So I need to do some quick conversions. So T1, I'm going to start with 25 degrees Celsius and add 273.15. And then T2, I'm starting with at 75 degrees Celsius adding 273.15. And I have to do that first before I plug in to the formula. All right, so our volume is 0.6 liters. Notice I'm keeping track of my units as well. I'm going to plug in T2, that goes up top. T1 goes in at the bottom. Notice how my Kelvin cancel out. I'm just left with units of liters. That's exactly what volume is. And now my volume is 0.701 liters. Now, before you move on, you always want to ask yourself, when it comes to gases, does this make sense? Does this track with what you know about the properties of gases? If I increase the temperature on a gas, what should happen to its volume? Well, I know from earlier that um, temperature and volume are directly related, directly proportional. If I increase temperature, the volume should go up. So yes, my answer does make sense here. If I had accidentally switched, say like these two terms, I didn't put them in properly, my answer would have been less than what I started. And that doesn't make sense. It's a good way to check your answer.